Hello and welcome to this session where we are continuing with our residence time distribution development. So when we introduced the types of reactors and we started talking about the internal and external RTDs, we first considered the plug flow reactor. And we know in plug flow, we have multiple plugs and they are all moving in a very regular way with the same velocity in each case. And so we said we had equal proportions of all the fluid elements at the different ages in our internal age distribution. We also said that they all exited at the same time, which was the space time of that reactor. So that's consistent with our drawing here. And then we also said if we were observing at the exit point here, we would find that all the fluid elements had stayed for the exact same period of time inside that reactor. And so they would all exit at the space-time tau. And that was how we drew it. We said there were no fluid elements of age younger than tau, and there were no fluid elements of age greater than tau, and everything was concentrated in a single instant tau. And we'll look at mathematically how to express that. We said that the Dirac delta function was relevant there, that we could use the Dirac delta function. So we look at how to express that just now, but let's just keep going with understanding the shapes to begin with. So the next reactor to look at was the CSTR, and I hope everyone has had a chance to try out what they think that should look like. But let's think about how, for instance, a pulse of tracer would enter and pass through the system. So if tracer entered, it would instantaneously mix perfectly everywhere in this reactor. So the concentration would instantaneously be the tracer concentration. So once we feed tracer in, it's better to say there's a certain number of moles that will enter in one instant, and then it will immediately fill the entire volume. So whatever the number of moles that were injected, the concentration becomes that number of moles divided by the reactor volume. So that would be our initial concentration of the tracer. And then as time passes, we can see that the tracer starts to exit here. And of course, some tracer will instantaneously be available at the exit and start to exit. And then as time goes on, more tracer will be exiting through the exit line here. And if we think about that, of course, it's different to what we have in plug flow. In plug flow, everything that enters will leave together, right? Because everything stays together. Whereas in the CSTR, everything gets mixed everywhere. So the tracer won't all leave immediately. Initially, we have a high concentration of tracer, so we may have a high concentration in the exit stream. But after that initial flush, we'll still have tracer in the system, which will slowly work its way out. So as time passes, because the tracer is mixed in here, it will slowly be leaving the system. And of course, while tracer has been pulsed in and it's leaving, we've got our the body of fluid is also passing through here. So whatever it is that, for instance, we mentioned water. So if water was passing through the system, it would keep going. We would have the flow rate Q here and here. So water keeps flowing. We've pulsed some tracer in, so that tracer has mixed with the water. And at all instants in time, tracer and water are exiting in this line. So as water keeps entering, it's diluting the tracer that's in here more and more. So the concentration of tracer is dropping over time because tracer is slowly exiting from this reactor. And so what we expect is that the concentration of tracer will drop in proportion to a curve like this. So we will have initially a high concentration of tracer. And because it's a high concentration, then we'll have a higher flow rate than at other times when the concentration will be lower. And so that concentration is dropping over time because of the serial dilution. So because water keeps entering and further diluting the tracer that was held up here, that concentration will go down. And so we expect to see a curve like this. And then I know you can see it here, but just pause the video and take a minute and think about how the exit RTD would look then. Right, so do pause, please. Okay, so hopefully you've said there that, yes, we would initially see a high concentration of tracer. And then as time goes and more tracer has exited the system, we would start to see that dilution effect. And so because also the concentration is the same inside and at the exit point, right? That's a feature of perfect mixing, nothing to do with RTD. Just for a CSTR that's perfectly mixed, the concentration in here is the concentration out there. So we would expect to have the exact same profile. And I know I've curved them slightly differently here. That's just an artifact of me not being able to point and click as well. But what we expect to see is that we would get the exact same curve there. So we see, even though the CSTR does have the curves, we expect to see them being equal. That's not generally true. It's definitely not true in the case of the PFR. And we'll look at a couple of other reactor types as well. But this is so far just according to waving our hands and imagining what might happen. So let's now try and do this using mathematical analysis. So let's develop a model. Let's start with the CSTR and then do the PFR. So if we think of a CSTR, right, if we think of our CSTR balance, then we can imagine a balance like this, right? We are putting some tracer in initially, so we can define the rate of change of tracer in the reactor according to this. So the volume we are expecting not to change, right? We know that the tracer is filling this volume and this volume is fixed. So if your flow rates in and out are steady, then the volume is not going to change. Of course, the tracer is unsteady. We are pulsing tracer in, but we are doing it in such a way that we are not upsetting the flow rate through the system. So this system is hydrodynamically stable, so the volumes and the volumetric flow rates are constant. So we pulse some tracer in, and then we watch it as it drains out of the system. So we have some rate of change with time of our tracer. So the rate of change is equal to the flow in. Now, after we inject the tracer, we are not putting any more tracer into that reactor. So for those who've done the RTD practical, you'll recall that after you inject a tracer, you never put any further tracer into the system. So this balance is being written for the time immediately after the time of injection. So the flow rate in is 0, right? The volumetric flow rate is constant. There's a Q here, but the concentration of tracer in is 0. So this flow in is a 0. And then the tracer is leaving the system. So there's a certain current concentration of tracer in the reactor, and the exit flow is Q. So that's the exit flow of tracer. So this is a complete material balance on our tracer. We also said the tracer is not reacting, right? The whole point of this tracer is only to look at the age. It's not at all to react with anything or anything like that. So there's no reaction term here. And there's nothing to prevent us doing this, right? This is just a material balance on the tracer. And this tracer, we've retained the accumulation term. We've said there's no flow rate. We've said there is an exit flow. So we said there's no inlet flow here. We know there's an exit flow, and we know there's no reaction. So this is the material balance on our tracer. So that is the concentration. And of course, we know that in a real, in the practical, you actually pulse the tracer in and you measure the concentration out. So that's fine. You can do that practically in literally a practical, but we can also, there's nothing to prevent us also doing it numerically or mathematically. So by writing this balance, we are saying we can also get the concentration as a function of time just by solving this equation. And of course, if we look at this equation, you can take Q divided here. So you can get a tau dc dt, and that's going to equal minus C. And so, of course, if we move the tau to here and we integrate this, this is nothing but the integral of, let's just create a new Word document here. Okay, let's do it in a new document, or let's keep working here. Okay, so we have dc dt, so dc dt equals, and we can see it's minus c over tau. And we know that the solution to this ODE is C of t equals C naught exp of minus t over tau. So that's the concentration as it varies with time. Now, we've also said that the exit RTD can be obtained in this way. The exit RTD is obtained as the concentration divided by the integral under the curve. So we've said E of theta is equal to C of theta divided by the integral, divided by the integral of C in theta. So let's evaluate this denominator, right? The integral of C in theta. Let's try and switch off the bold. I don't know why it keeps becoming bold. So the integral of C in theta, we can just write it like this, the integral of, and so we have an expression for C in theta. We can write this as C naught exp of minus theta. So that's minus theta over tau in theta. We can see that's going to equal. So the integral, here we have a constant. We can extract that constant of integration. And we can integrate the exponential of this function as minus 1 over tau times exp of minus theta over tau. Okay, so we can write this as C naught, and then minus 1 over tau. So we'll write here minus C naught over tau times exp of minus theta over tau. Okay, so just check that you're happy with that integration. Well, in fact, there's an error here. It should be tau times, not, so it should be C naught times tau. And just check it. If you differentiate with respect to theta, then you're going to have minus 1 over tau times all this. So the minus 1 over tau cancels with this tau, leaving us with a 1 times C naught. So in the end, we would get back the same expression here. So that is the integral. And of course, we are doing this between limits naught to theta. So let's go here. So this is lower limit is naught and the upper limit is theta. And so we can look at this and realize that at 0, this is the exp of 0. So that's a 1. So we can write all this as C naught tau. And well, there's a minus sign out here. And then we are evaluating this at theta in the upper limit. So this is just the exp of minus theta over tau. So that's the upper limit. And then the lower limit, we have a 0 here. So this is going to be -1. So that's our function. That's the integral in our denominator. And then if we if we take the limits 0 to infinity, remember, this is the general limit if we were going 0 to theta. But if we go instead from, if we let theta be infinity, right? So let's imagine the case where theta is infinity. So we write here, so theta tending to infinity, then we can see we are going to get here the exponential of infinity, of -infinity. So x of -infinity is a 0. So we regard when theta equals 0 as this is 0. And then we've got -c0 tau times a -1. So the integral from 0 to infinity, remember those are our limits here. There's a lower limit of 0 and an upper limit of infinity. So we pick infinity to be our lower, we pick that to be our upper limit. Those are all the possible ages. Okay, I'm not going to write it in there. We know we are integrating over all possible ages. The lowest possible age is a 0, right? You can't have negative ages. And we don't know what the upper limit might be. So instead of trying to prescribe an upper limit, right? Remember, space-time is more like the average time that we spend in the system. But what we need here is the upper limit. We want to integrate under the entire curve. So generally speaking, we'll just use an infinity. So that's why we are looking now at theta tends to infinity for this integral. And we've seen at infinity, this is a 0. And so we're left with the -1. -1 times this gives us c0 over tau. So if we look at our E of theta, and yeah, let's just copy this through. So this E of theta is equal to, and we can see a C of theta up here. So here's C of theta. Well, it's C of t. So we'll just change the variable to be theta. So that's what we have here. That will be the numerator. And then in the denominator, we've seen that we have c0 tau. c0 tau. And so the c0s will cancel, leaving us with this expression. Leaving us with 1 over tau x of minus t over tau. And actually, we use theta here. So we change the variable to theta. Remember, t0 we define to be 0, the time of injection. So this is a theta. And so this is a theta. And now we see we have an expression for our exit RTD. Let's just copy this as its own expression. Because we can see now that this expression is totally independent of the tracer. So I'm just cutting out the intermediate steps here. So we can see E of theta is 1 over tau x of minus theta over tau. We don't see any concentration of tracer in this expression, right? It's purely in terms of the space-time of the reactor and the independent variable tau. So this is what we expect, because we don't expect the age distribution to depend on the tracer. Remember, this age distribution refers to the fluid. We were doing the tracer experiment because we want to understand the age distribution in the fluid. And now we do have an age distribution which is independent of the tracer and which we expect to be the same as the fluid's age distribution. So this is the age distribution in our CSTR. Also, if we look at the form of this, you've got a constant here times an exponential decay. And if we look at what we drew here, we said we do expect an exponential. Well, we didn't say exponential. We knew we'd start at some high concentration and it would drop over time like so. And an exponential function does have this form. So this is in line with our expectation as well. We had also said I should equal E. Now, let's not assume that, right? We did derive last time an expression relating E and I. So we had said that generally speaking, I of theta equals 1 over tau. And this was of 1 minus the integral going from naught to theta of E of theta in theta. So just look back and see that this agrees with what we derived, right? So we said there exists a relationship between I and E, and this is the relationship. So let's now use what we've derived here to develop the expression for I. So I'm just going to say this is equal to, and let's substitute for E of theta there. So E of theta in the case of the CSTR. So let's say this is specifically for a CSTR. So this is general, but now we make it a CSTR by using this for E here. And we can evaluate this integral. Again, it's the integral of an exponential. You've got a constant out here. And then the integral of this is going to be minus tau times all this. So let's evaluate that. So we know that the integral here is going to be minus tau, right? Think about it. If you've got x of minus theta over tau, then if you multiply by a minus tau out here and then differentiate, it would be minus 1 over tau times that new tau, and that would give you back this function. So we know that the integral of the exponential of minus theta over tau is equal to minus tau times x of minus theta over tau. So the minus tau, we can multiply by 1 over tau here. That will give us a 1. And then that minus can cancel with this minus, and we get a plus here. So we've canceled this part. And we've got this as the exponential. And we are evaluating between these limits, naught and theta. So that's our integral. I don't know if maybe I should use a few more steps just to make it a bit clearer. So let's put in an intermediate step just to double check that everything's right. So that's the same step. The integral is going to be minus tau. So let's first extract this part. And then when we integrate this, we can see we are going to get minus tau times this. So we'll write this here as, so we'll take the integral. So let's integrate it. So this integrated will be minus tau times that. And we can see this minus tau times this minus 1 over tau gives us a plus 1. And then left over is x of minus theta over tau. And we are integrating between limits naught and theta. So let's stick those limits in. So this is naught to theta. Right, and so we can see that's the same as the expression there. And thinking about this, we've got the upper limit at theta. So this is x of minus theta over tau. So there's nothing we get rid of here. Minus, and then the lower limit is x of 0, which is a 1. And so we can see the 1's canceling here. So let's just do it piece by piece. So the upper limit will give us exp of minus theta over tau. And the lower limit will give us, it's going to be minus, and then it's exp of 0, which is a 1. And now we've done all the work of, then we've applied the limits, and we don't need this piece anymore. Let's just see. Okay. It's going to, yeah, it's not going to go away. Let's take this out here. And then this one is a minus 1, right? So once more, it's 1 plus, and then applying the upper limit, it's exp of minus theta over tau, and then minus the lower limit, exp of 0, which is going to be a 1. So x, and then your minus 1 here. Then we've got plus 1 and minus 1, so those can cancel, leaving us with and now we can see it's 1 over tau, exp of minus theta over tau. And that is the same as E of theta. So this is the exit age distribution for a CSTR. That's what we derived here. And now when we applied the general relationship between E and I, noting that E has this form, then we get 1 over tau exp of minus theta over tau, which is the same function as for E. And we said we do expect that. We expect, because of perfect mixing, the age distribution at the exit is the same distribution inside. So we do get that same result. And it's surprising, right? Because this operation is, it's not quite elementary. And this function is also not quite elementary. But if you work through, you'll see in essence that this function, this specific function, is an identity of this operation. So mathematically, that's how we can express it, that we have an operation and there's an identity of an operation. In other words, a choice which gives you the same value. So for instance, in multiplication, an identity of multiplication is 1. If you multiply 1 by something, you'll get the same thing out. Similarly, in addition, 0 is an identity of addition. So you add 0 to anything, you get the same thing back. So in this case, the identity of this operation is this expression. And it's only the case that in the CSTR that we get this exponential decay with this 1 over tau. So that's the only time we get that. We saw for the PFR, it was quite different. So this is the one case where it's the same. Okay, so that's how we can get our CSTR RTD. And then going a bit further, we now also want to express our PFR RTDs. So for the PFR, we said that we expect our exit age distribution to be this Dirac delta function, a function that's 0 everywhere except at some value where it's going off to infinity. And so the Dirac delta function, strictly speaking, is defined like this. So Dirac delta, let's see, Dirac delta function, it looks like this. It's defined that f, let's do it here. So f of x, where x is not equal to 0. When it's not equal to 0, then f equals 0. And when f equals 0, when f equals 0, then this number is going off to infinity. But it's going off to a special infinity. It's not going off to a random infinity, if I can say it that way. It's going off to infinity in such a way that if we were to integrate under this curve, so if we were to integrate from minus infinity, minus, let's see, minus, no. This is the integral. And okay, let's just make it 1 and 1 and correct it. So this is going to infinity, and the denominator is going from minus infinity. So yes, f tends to infinity when x equals 0, but it goes to infinity in such a way that the area under that single point is a 1. And as we mentioned in class, think about a normal distribution function where the standard deviation is going to 0. So think of a normal distribution function which is getting thinner and taller. So we know the area under the normal distribution is always 1. And as it gets thinner and thinner, to preserve that the area is a 1, the maximum point must go off to infinity. So that's how you can smoothly get to a Dirac delta function through a normal distribution. Just let the variance go to 0, the standard deviation, let it go to 0. But anyway, this is strictly how the Dirac delta is defined. So for our case, we have not quite the same. If we look at our E of theta, our Dirac delta is not centered on 0, it's centered on a tau. So we have to shift our arguments here. So we'll simply state that E of theta for our PFR, so E PFR of theta is equal to the Dirac delta function. So Dirac delta, and the variable in our case is theta, and we need to shift it by tau. So that's the function for us for the plug flow reactor. That's the exit age distribution. And of course, if we look at our function here, it's exactly that, right? So it's 0 everywhere except at tau where it's going off to infinity. So that's our Dirac delta function. Now, of course, what we want to do is get I of theta as well. And we said I of theta, the general relationship is 1 over tau of 1 minus the integral naught, and I'm just going to say naught and correct it. The naught to theta of E of theta in theta. And so that's our general relationship between these two. And in this case, in our PFR case, we'll have this specific form. So I PFR is equal to, and our E function is this one. So Dirac delta. Now let's think about what happens in this integral. So imagine different values of theta. So basically we are integrating. Okay, let's talk about it here. So we've got some E function, and as we consider different theta values, so if we start at theta equals 0, then that's 0 to 0, that's a 0. Then when theta is a bit bigger, then we have to integrate that section of E, and we keep changing theta and adding up the integral up to that point. So if we think about our Dirac delta function, we can keep adding up the function. So we keep integrating under the curve. And Dirac delta, if we keep integrating here, we're going to get 0. It's not adding anything to that integral because this is a 0 here. Then suddenly we get to tau, and the function jumps up to, well, it's going up to infinity, but it's going in such a way that the area under this is a 1. So when we integrate across this point, we get our integral jumping by a value of a 1. And after that, we only get nothing added to the integral. So the integral jumps up to a 1, and then it stays on a 1 because there's nothing else coming in. So if we look at what we have here, it's going to be a 0. This integral will be 0 up to tau. At tau, this will jump to a 1. And then after tau, this will stay on a 1. And if we were to draw that, it's like this. So if we imagine the integral here, let's do this with lines, I guess. So we can, let's just use something here. So the integral under this curve is going to be a 0. So it's going to be 0. And then when it crosses this point, it adds an area of 1. And then we get a value of 1, and then the 1 continues there. So that's going to be our E of theta. That's going to be the integral E of theta. Now, what we actually have is 1 over tau times 1 minus the integral. So if we look at 1 minus the integral, then this is 0. So 1 minus 0 is a 1. So we'll have a 1, and then we reach the stage where it becomes 1. Then 1 minus 1 is 0. So it goes down to 0. And then, of course, we have to multiply the whole thing by a tau. So, of course, I'm talking my way through this equation. I'm saying 1 minus the integral. So this is 1 minus the integral. And then times 1 over tau. This is not 1. This is the integral. And then 1 minus this is 1 going down to 0. And then times 1 over tau. So we get a function like this. So we can see we are getting the integral that we expected here, I of theta. So we had talked our way through this. We know how to get I of theta. And we can also define a special function. So in maths, we do define the so-called Heaviside function. So the Heaviside function, I don't know how to make the curly H, but it's got a little bit of a curly H, which I'll draw when we are in person again. But the Heaviside function is defined that for theta less than 0, it's equal to 0. And for theta greater than or equal to 0, it's a 1. Right? So it's kind of heavy on one side. So that's the Heaviside function. So for theta greater than 0, it's a 1. And this has been used in conjunction with the Dirac delta function. So if you were to integrate the Dirac delta function, you'll see you'll get 0 until you hit 0, and then past the 0, you get a pure 1. So the integral of Dirac delta is a Heaviside function. In our case, we can write this as I equals, and it's 1 over tau. 1 over tau. I equals 1 over tau. Okay. Here. 1 over tau. Yeah. So in our case, we have 1 over tau, and it's going to be 1 minus the Heaviside function. And we have to shift this by theta minus tau. So work through this and see that you agree this is the same as our I of theta. Okay, so that's how we get E and I. So we hopefully understand our way through these graphs, and then that's how we derive these shapes. That's how we get the actual functions in terms of the PFR and the CSTR. Okay, so with that, we have said before that we regard the PFR and CSTR as opposite extrema. The PFR is where everything stays perfectly together. The CSTR is where everything is perfectly spread out. So we anticipate that now that we have all these functions, we'll be able to connect them together and start to simulate certain real-world reactors. And we'll start looking at that next time. So thanks for listening. See you next time.